All right. So welcome back. This is the exercises 201 and 202, the simple quantitative models. I'm guessing you're all thinking, all right, we're finally going to get to the important part of the class. Just like to say, you know, again, by the time you've gotten to this step, your fate is really sealed. By the time you're doing a regression, you're either going to be successful or not based on what you're going to take into this regression process. So I'm hoping this part is not anticlimactic for everybody, but it's got a lot of options, and it really starts demonstrating what kind of information we're going to be getting out of the spectra. So up till now, we've been working kind of with flat files and some graphics and whatever, and now you're going to see the predictive power and the information that is actually in the spectra. So let's jump in. So first, we're going to start looking at some of just the operation, the practical aspects of calibration and help you through the software. When you get into the quantitative model feature, when you've got an SVF file or a spectral file open, you can just click on Calibrate from the top menu and choose quantitative calibration. You need to make sure that your file is correct. Go through a couple of file I/O type things. Make sure that your output file is correct. And generally, you're going to press the Calibrate button and wait for the processing to end. Now, that's a typical way of doing it. I'm also going to show you how I do this, which is I like to pause and go through this a little bit manually. I like to see what's going on. Then we'll take a quick look at the statistics. And in general, this process goes pretty quickly. In the past, just being involved with near infrared was a justification always to get one of the fastest computers that are out there. In general, the computers are so fast right now, unless you're working with very large data sets, you know, a medium, high, you know, a decent CPU and amount of memory, and you're going to crunch through these data really quickly. So getting into the quantitative calibration program, it's just here from the menu. You've got a file I/O box. You've got some options. We'll be talking about the minimization file towards the end. Also expansion file and validation file. We're not going to talk about that right now, but this is your input file. And if you want to, you can save a file that is this file minus any samples that have been thrown out as outliers. Okay. So this is going to be your output product file here. Okay. You've then got from the options button, you've got all of these options. If you notice, you've already seen the top part of this box. You saw it in graphics and in plot. Again, these are the exact same math treatments that you were visualizing back in that section there. We've also got additional regression parameters. Again, the help section has got really good information here, but I'll talk about those in a little bit. My demonstration for this exercise is going to be a little bit longer than some of the other ones. We're then going to go in and view the results. So you've got various different graph types that are available. You can look at just your calibration samples. You can filter it just to see your outlier samples, or if you've got an external validation set to see just your validation samples. You can see your reference value, your predicted NIR, any deviation or difference, your t-stat, where you are in the constituent range, and your global neighborhood distances. We've discussed where those are. So those are describing how well your sample fits in the population and how close is its nearest neighbor. We've also got then a number of metrics or calibration statistics. Finally, there are our press values. We talked about press plots when we were doing quantitative data analytics. So this is a residual error, some squares, and we're plotting it per factor. And if you remember, we're looking for that low spot in the press plot where we're getting the most information possible from our spectra and from our calibration set, but we are not overfitting. So we're going to be using this press plot and our graphics in general to try to determine how many factors we will use in our final calibration. Then we will output a PRD, our product file, and you've already seen these. So now you're going to know where these statistics come from. Okay, so per constituent, you're going to have column per constituent, samples that you kept, samples that were rejected, the number of factors we've selected. We now know what the factors are, and your calibration stats. Okay, you've also got a 3D display that you can access from right within your PRD file. It's right here. You can go in and plot your samples, and you can determine, specifically what has happened. But this is based on your PLS scores that are, looking at your various constituents. So this is slightly different than the PCA plot that was looking at the spectra only. Okay. Then there's also a key part of this, which is your offline prediction. So this is an area where you can take a spectral file, your SVF file, a PRD file, and do a prediction and a comparison back to your reference values that are present in your SVF file. This is also the area, if you remember when we were talking about file types, where you can export an AVF file. And this AVF file has your sample predictions, the NIR predicted values. The AVF file is optional, but this is a place where you can go in and you can cut and paste and drop it very nicely into an Excel file if you want to do any external processing. You can also change control limits, and it gives you kind of a very nice XY plot for seeing your results. When you look at your monitor, it pulls up this table. And again, it's very similar to the table that you found during the regression. Control limits and graph options are here. There's also an area where you can go in and manage your equation, your PRD that you've made. So for some reason, if you are creating a PRD from multiple SVF files for whatever reason, or you want to rearrange or even rename your constituents in your final PRD file, you can do that here. You've seen this before. You open up your PRD and you've got your area. You can go in and delete. You can change your constituent names. You remember we've got a flag that indicates the moisture basis. If you delete, it's going to give you a warning. You can go in and view the samples, again, viewing the PLS mathematically reduced space, not the PCA scores from within your PRD file. Okay. So we're looking at moisture here. Okay. So we've got a couple of exercises. The 201, just go ahead and make a simple quantitative model. It will walk you through this step-by-step, including the options that you should take, and then go in and do an offline prediction with monitor, okay? For the second one, it's a little bit more complex. We've got a hay model. We've got different parameters that we're asking you to select. If you'd like, I mean, this is up to you, but if you'd like to, you can focus on protein only. And once you've made the PRD, go in and look at the statistics and do an evaluation with monitor, okay? So it's a slightly different way to look at it. All right, we're going to make our first model. So we can go into Project Manager and collapse all of the Section 1 exercises. We'll jump into Section 2. And we can start out with our basic building here. I'm going to start out with just the first flower model. We've done all of this before. We've seen the reference values, we've plotted, we've done everything. Now we're going to use, for the first time, our calibrate option up here, calculate quantitative calibration. And as you can see, the output file name has been put in for us. That's a PRD. If you would like to change it or change the location, you can. So for example, I can call this one demo, if I can spell. So this is going to be the path where I'm storing the model, and then the output file is going to be named this. Okay, if I want to, I can store a new base file. That is going to be my input file minus the outliers that have been deleted. And we'll talk about these options later on. One thing you really want to look at every time you do a regression is to open up this options screen. Again, we've seen this top part before in plot. So we've got our derivatives here and our different scatter corrections and data set corrections that we can do here. I would recommend that everybody uses this. It's our standard way of calculating. And again, this is going to get you 90% of the way there at least. It's a good first place to start. For regression types, we've got a number of different regression types. These are all explained in the help very well. Up until UCal 4, so our previous versions, our standard way to go through this was PLS. It's a classic partial least square regressions. We now have, with UCal 4, a variance scaled or VPLS option. The variance scale PLS scales an intermediate step based on the variance present in your constituent values. And again, this is explained in more detail for those of you mathematicians that are out there. But in practice, we find that variance scale PLS never hurts you compared to the classic PLS, and in general is about 5 to 10% better performance than a classic PLS. So for my investigations in general, I use variance scale PLS always to start with. Maximum number of factors, this is set as a default based on the number of samples you have in your calibration set. If you want to, you can bump this up a little bit more. It just increases the processing time slightly. But generally, you're going to select your PRD to use fewer factors than your maximum number, okay? You've got different ways of doing cross-validation. Generally, we use a constant. It's a particular pattern through the file. These, again, are outlined in our help. But if you've got prior knowledge about your data set and you want to do a particular type of cross-validation, for example, a block, or you've got some other validation set, you can use this as your different options here as your cross-validation. Number of cross-validation groups. Again, going back to an earlier lesson, if you remember, when we've got a large number of samples, we can afford to use a smaller number of cross-validation groups because we are still getting a significant number of samples in our regression area. These files are pretty decent size, so the cross-validation groups will jump up to be 4 or 5 or something like that. If you've got a very small number of samples, you're going to want to raise the number of cross-validation groups to go up here. There also is an option in the software, which is 0, which is leave one out. So in this case, you will have the number of cross-validation groups equal to the number of samples in your calibration set. If you're doing an initial investigation, and you've got like 30 samples and you just want to do a feasibility study, for example, you might try 30 samples. I would never put a 30 sample calibration. I shouldn't say never. I would be reluctant to put a 30 sample calibration set into production unless it's a very simple sample matrix that I can easily explain with a small number of samples. But I might want to determine, hey, am I making progress? Does this road look promising, or should I abandon it? It's not a good application for near infrared. In that case, I might get 30 samples and do a quick calibration and see what it looks like. If you've got 30 samples or a low number of samples, try leave one out. It's going to be your best option. The number of throwout passes. You can set the software up. In general, we do to evaluate your outliers based on these limits that you set down here. And if you find any outliers, throw them out and then go back in and do a second pass through with your reduced sample set. It's a way of refining your data set and throwing out your growth outliers, okay? So that's, I would generally leave that at 2. For this, I oftentimes will jump up my, my maximum global distance to 5 from the 4 default, sometimes even 6, depending on how early I am in the calibration development process. If you are overly strict, you will make a calibration that has a very narrow range of spectra in it. On the other hand, you don't want to include samples that are so different that they don't belong in your calibration set. So there is a gray area here. Somewhere in the 5 area is where I normally start out with my maximum global distance. And for my neighborhood distance, I sometimes will move this up to 0.7 or 0.8. I just don't want to be overly strict in throwing out my samples, especially in my initial investigation. I want to see what's happening. Missing data value, leave that as the default, or I would. And so anything with 3 zeros like this is going to be treated as a missing data value and it's going to be ignored, okay? If you remember, if you've got a real value of 0, we recommended that you put it in as 0.0001 or so, okay? That will still be included in your regression, okay? Let's take this off right away. We've got our data sets and we're going to be using all of our constituents. You can select this. I'm just going to look at protein right now to make this quick for this demo, but you're going to want to do them all. And then for our wavelengths, we're going to use this segment, which I think is the range of the SVF file. You can edit these segments or you can add segments. So you can just double click in there and edit those, okay? And we're going to go in and run this. Just as a note, once you get more comfortable with all of this, UCAL4 does allow for batch processing, and you can set up, for example, a sequence of 6 of your favorite permutations of math treatments. And you can set it up, go to lunch, come back, and it will evaluate all of those for you. So that's batch processing. So again, I've taken out this pause, and I'm going to click OK, and I'm going to go into calculate. So we jump right into the regression. You can see the progress bar going across. It's going into a calibration phase. And this is going to take about 45 seconds or so. We did set this up, if you recall, to do a number of throwout passes being 2. So it is in the background going through this iteratively. So it will go through the process. It will do the mathematical reduction. It will find the eigenvectors. It will score all of the samples according to that. It will make the regression. During that regression, if it finds any outliers, it's going to throw them out and repeat the process up to 2 more times. Okay, and this is the output. So you can see we've done a nice job. It's a simple XY plot. You've got your table here of all of your samples. If I want to, I can look at my outlier samples. So these 3 samples were thrown out as outliers. This is useful to find out why they were thrown out. You can see, for example, if I would have had an outlier limit of 6, for my global distance, that this sample, 600A, would have still been included. And in fact, the deviation is very small. It's a well-predicted sample. It also has a neighbor that is fairly close at 0.49. So in fact, this is a sample, in reality, I might want to keep. It's just useful to go through your outliers and find out why they're being thrown out. Oftentimes, you're going to find a global distance of 10 or 15, or you will find a p-value of 3 or 4, a sample that is just way out. So it might have had bad reference values, for example. Those ones you want to throw out. Those, those are great. But this one, for example, I would assess as being on the line. Okay, we've got our press plot down here. It selected 7 factors. So it's tough to see. This is very low errors. But if you notice that the press plot is going down and it's down here, it popped up a little bit at 8 and it's going back up again at 9. Not all of your press plots will be this pretty and this simple to evaluate. But in this case, you can see why the software selected 7. It's got logic in it to evaluate your press plot and try to choose the best number of factors, okay? And in this case, I think 7 is reasonable. I would never move forward. If anything, I might back up and looking at this plot, I might say, I'm doing a reasonably good job with 5 factors, and I know my calibration is going to be more stable with 5 factors. So, this gets into a judgment call. You will be penalized by instability if you have too many factors. Remember, that's overfitting. You will be penalized missing out on a tiny bit of performance if you do not use enough factors. So we're trying to find that optimum level. If we then look at our statistics here, we're evaluating our calibration performance. So this is how I evaluate calibration performance. One of the things I look at is my standard deviation of my reference set. Remember, we saw that in the graphics, in the histogram. That's telling me that that's the standard deviation of my reference data. I then start looking at my standard error of cross-validation. If the standard deviation in my reference set is similar to the standard error in my cross-validation set, the instrument is not helping me. I'm literally throwing a dart, okay? The distribution of values, the standard deviation in my reference data is about the same as I'm getting from the NIR. The NIR really isn't helping me, okay? So I'm always mentally making that comparison. In this case, you can see that the standard error of cross-validation is 0.2 compared to 2.8 almost. So this is, this is fantastic. We're getting a really great result here. Okay, the statistics are all explained in the help, but I'll go through them real quickly. So this is your standard error of calibration and your R-square of your calibration set. This is the fit. So these are the statistics looking inwardly in the middle of the calibration process of the calibration set predicting itself. So this is an overly optimistic view, but this is describing the fit of the regression on itself, on the calibration set that the regression was based, okay? So I take the SEC and the R-square with a grain of salt. The next two are the two that I really key on, and that is the standard error of cross-validation. Remember, that's approximating an independent validation set, and the R-square of the validation set, of the cross-validation set. These two are really indicating the kind of performance you're going to find in real life, okay? So I make a mental comparison between this standard error and this standard error. Your cross-validation error is always going to be higher than the calibration error in your calibration set, okay? And again, I'm going to use this number. I'm not going to use this. I would never tell an end user my SEC values. I would tell them my cross-validation errors, okay? So these are the two that I'm looking at really to indicate how my calibration is going to perform in real life on unknowns. The only true way to do that is with an independent validation set, but that requires more reference samples, okay? So for in the calibration process, I'm going to trust this. In between these two, I'm going to trust my standard error of cross-validation. That's indicating to you and to your end users the average error, the standard error that they can expect when they're making a measurement. The R-square of the correlation is nice, but the R-square statistic is highly dependent on range. Okay? So if you've got a very long range, a very broad range, your R-square is going to look fantastic. If you've got a very narrow range, your R-square will not look as good. But in the middle of it, what really matters to your users is how accurate are my values, how accurate are the results, and that's your standard error cross-validation. Okay? You do have min-max values and mean of your reference data. You also have some other information that's out here. Your global distance is 1, obviously, because you defined your mathematically reduced space. You defined it based on this set. So the global distance is 1, and your nearest neighbor is 0.08. Okay, and it shows your math treatments. So that's how I go through and I evaluate this. If I were to click here on Write PRD, that calibration would be written and we would be done. I'm going to cancel that and I'm going to go back into options. So let's leave this the same. I do uncheck mean center most of the time. My indications are here, and I just want to show you one more thing before I end this lesson. And I will be doing this one more time. At the end, I'm going to go through and have a quick lesson, a quick lecture about putting it all together. And I will run through this one more time. But here, you can also check to pause to preview the calibration results. And I like doing this just so that I can be in the middle of this and see what's happening. So I forgot to change this only to protein, but we're on moisture. And one of the things that you can see is that it's stopping and looking at the number of factors, okay? Now I can manually select the number of factors. Here I've got my press plot. This one is very definitive, okay? I've got my errors going down to factor 4, and then my errors are climbing back up. So this is easily my optimal number of factors. You can also put on the y-axis, you can look at your errors. You're going to find that these track, and almost always your correlation is going to follow a very similar pattern, though it's inverted because we want a high R-square, whereas we want low errors. Okay, so I'm going to select number 4, but you can see if I want to, I can change the number of factors that are going to be used in this. Okay, and you can change that my red one has changed, and my highlighted row here is changed. We'll leave it at 4 factors. We'll go forward. We'll go to our next constituent, and we get the same thing. So what this does is it allows me to see what's happening during this process. And I like picking my number of factors. Every once in a while, UCAL4 will pick a factor either higher or lower than I'm comfortable with. Okay. In this case, for example, if we look at the press plot, and we look at the values that are up here, 4 and 5 are virtually identical. There's no way that I would pick 5, an additional factor, because it's not adding any performance. It's only adding complexity and increasing my chances of overfitting. Okay. So one of the reasons I like to do this manual and use the pause to examine results is if in fact it had picked number 5 here, I would back it off to number 4. Again, you're going to get penalized only slightly on performance, but overfitting can lead to unpredictable results. And overfitting is something you really want to avoid. So I like to pause to examine the results. I'm going to accept number 4 here. It's going to move on to my last constituent. And we saw that it picked 7. And you can look at the standard errors. So the other one that I might pick would be 5. And you can see that it's 0.225 versus 0.21, really. Is that significant? Maybe, maybe not. That's a call that you're going to have to make. But in general, I try to use the smallest number of factors to get, approximating my optimal or my best performance. Okay. When in doubt, I will go with a lower number of factors just because that will lead to long-term stability out in real life. So I can go ahead and click this. I get back to this display, which we saw. Now, since I've got multiple constituents, you can see that I can select the various constituents. If I'm happy with everything here, I can go in and write my PRD. The PRD was written and it's done. The last thing I will show you is, and I now made that demo PRD, okay? The last thing that is important is we're gonna open up that, we're gonna go into monitor. All of the rest of these are described in the help file. And these are pretty advanced when you're gonna wanna be doing some of these other comparisons, but the top one you're going to be using all the time, Spectra in a product file. So this is how you're going to be doing your offline predictions. You can see that it filled in our input Spectra file by default. This demo PRD I just made. If I want to, I can generate an AVF file. I can set the limits if I want to. I don't. Sometimes if you don't have your constituents perfectly matched, a screen comes up asking you to match your constituents. Go ahead and go through that. For example, if you've got PRT in your SVF and protein in your PRD, you might have to do a manual matching there. And one other thing is that if you're doing this offline prediction and your SVF file does not have reference values in it, this screen will be blank and you will have to click display all samples, okay? So this is showing your predictions. It's doing an offline prediction. You've got your reference values from your SVF file, the NIR predictions, the deviation or difference, your t-value based on your constituent prediction. You can see that this one has a significant t. You've got your global distance and neighborhood distance. We are predicting the calibration set. So our neighborhood distance is 0 because these samples that we're predicting were present in the calibration set. So we're predicting against samples that are present in our calibration file. But if you notice, there is one here. This one has a neighborhood distance of 0.018, but it's also got a t statistic. It's a t outlier. So this one was thrown out in one of our outlier passes during the regression, but it's still present in our SVF. So that's why this one has a neighborhood distance, whereas all of the other ones have a neighborhood distance of 0. Okay, you can go in and you can graph, and it will show you your XY plot, shows you your correlation. It gives you a slope and intercept. It also shows you your reference in your NIR. So there is a tiny bias of 0.1%, 0.14% bias here. So it's a good way to visualize on your graph. One of the things I like to do is to put out my limits. They're based on the regression itself, and also put out equal axes so that it just scales the XY plot in a consistent perspective. So you can see that this calibration has done a nice job with moisture. I can click OK. I can go in and evaluate my other constituents. Let's take a look at protein. I can go in and graph. Once again, for my options, I'm going to make sure I've got equal axes and set my limits. And we've got this kind of a prediction for protein. So very nice to visualize. And that is our walkthrough with the simple quantitative regression. There's a lot going on here, but I think you can see that we're presenting a lot of information that you've learned about in your previous exercises, in your previous lessons. So now you understand what the regression is seeing. You understand that we're mathematically reducing the data. You understand where the press plot, what the press plot is telling you, and how we're preventing overfitting. We're looking at outliers. We're looking at global distance, neighborhood distances. You know how they're being calculated. You understand what we're doing in cross-validation in general. We're using that as a system to evaluate the performance and to prevent us from overfitting. to make sure that we've got stable predictions for our unknowns once we release this calibration into production. So this has been a longer presentation of the exercise. There is a lot going on, but what's going to happen over time as you start making your calibrations, you're just going to get a comfort level with this process. So I hope you enjoy this, and please proceed to the couple of exercises that we have and start working with the simple quantitative regressions. Thank you.